Hi there, this is Andrew Brody with Yokogawa's Network Solutions Group, and today I'm doing the follow-up video on my paper called Simplified Curve Fitting for Renewable Energy Data Collection and Control. And what I'm going to cover here today is the two examples that I talked about in the paper, where essentially I have methane correction flow for a landfill gas monitoring system, as well as correcting the angle on a concentrated solar thermal power collector. So if we take a look here, I've got the two tables of my what I'm going to create kind of a function that's going to approximate the lookup for the correction here for the thermal mass flow meter, as well as what I'm going to do to match up my angle reading from my inclinometer or encoder against what's the actual angle of the receiver. This is the pipe that flows the thermal transfer fluid for the concentrated solar power collector. So if we take a look here, we can see here's the percent methane that I would get from a sensor, and here's the correction factor that the manufacturer of the thermal mass flow meter has asked to apply to essentially correct the overall flow to give me a reading of the methane, or kind of the greenhouse gas that I'm going to be either burning off or flaring. Over here is the results of a curve fitting function that I'm using to approximate the lookup table. And over here is the difference between the number the function generated and the actual correction factor. And we can see that it gave pretty good results here. Same thing over here. We can kind of see that when the solar collector is at flat, we can see there's maximum displacement, or kind of a difference between the receiver. This is once again the pipe that flows the heat transfer fluid. So due to kind of gravitational torque on the receiver as it hangs out, we can see it's got kind of maximum displacement from the angle sensor at its two extremes of movement, the 180 and the 0. And we can then see over here kind of the percent difference that I'm actually getting based on my function. Alright, so how do we arrive at the actual functions? There's several ways of doing it. One of the ways that I use is a free website called ZunZun.com. But if you do a Google search on function finders or curve fitting function finders, you'll be able to come up with several other alternatives to this that include kind of applications that you can buy, or often they have demo modes. But I'm going to use ZunZun as an example here. And the two types of functions that we're going to be interested in are 2D functions. You could think of this as a table with two variables, where you're going to have your input variable and your output variable. For example, in this case, the input variable for one of our examples is going to be the percent methane from the sensor, and the output variable is going to be the correction factor. For the solar tracker, our input variable is going to be the angle from the sensor or inclinometer encoder, and the output is going to be the correct angle for the actual heat transfer fluid pipe, the receiver. So that's kind of a standard f of x, which is x is your kind of input value and y is your output value. F of x equals y. And then over here we have 3D functions. This is kind of like f of xy equals z. So you could think of two input variables used in a function to generate an output variable. So x and y equals z. So a typical one we'd find in industry would be something like pressure, temperature equals maybe like a volume correction. So we might see something like this for steam, or certain gas volumes and so on, where the actual volume is going to be affected by the pressure and the temperature of the steam or the gas we're taking a look at. Okay, so once we get here, I go straight to function finder. And once I pick function finder, I pick 2D function finder. And then there's going to be a few things that we're interested in. The first is text data editor. All right, and this is where you're going to put in your table of data. So typically it's going to have an example in here. You just hit clear all text and paste in your data. So you could go clear all text, go back to my Excel spreadsheet, and I'm gonna go ahead and copy that data, and I'm gonna go back here and paste it in. And so that's how easy it is to input your data from something like Excel or wherever you want to cut and paste it in. Next place you'd go is your fitting target. This is the way it's going to calculate its error between what you put in as your variables and the function it generates. So between kind of your lookup table and the actual table it's going to generate with its function using your input variable. All right. Next thing is you can go ahead and put in your labels. So I could go %methane, and over here I can put in something like correction factor. The next thing we could go ahead is smoothness control. Generally, the more coefficients, essentially the more parts to the equation that you allow it to generate, the better it's going to be a fit. However, on the other hand, the harder it is to enter into a data acquisition system or a control system, because you're going to have to build up a very big function. So generally what I try to get away with is I look at maybe 3, 4, or 5. I'm going to go with 3 coefficients. All right, and then I'm going to next go down to this equation family inclusion. You can see that ZunZun looks through several different families of equations to try and find a function that's going to best fit up with your data. To speed things up and get rid of a lot of functions that are kind of a real pain to enter into typical controllers and data acquisition systems, I'm going to get rid of some of these. Feel free to try them all. ZunZun also has an affinity for polyfunctionals. This is including logarithmic functions, trig functions within the actual function it's going to generate. And sometimes, especially controllers, they may not have a trig function like all your sines and atans and cosines, stuff like that. So I'm going to get rid of those as well. In fact, I'm going to get rid of everything but polynomial. Polynomials are generally easy to fit in and match up with most curves or table lookups that we're going to run into. Okay, and then I'm essentially going to ignore the rest of this. And once I've kind of set up all that, I'm going to go ahead and hit submit. And because I don't have as many families to look at, it's going to go through and generate a series of matches that are going to match up pretty quick here. All right. If you left it open to all the equations, it can take a little while to generate. So you can kind of see here's some of the potential solutions that it has come up with. And so this is the type of equation you'd be entering into your controller or data acquisition system. And you can see some are better fits than others. So here's our top choice right here. It's a pretty easy equation. You could think of x, that's going to be your input variable. So in this case, it's going to be your %methane, or it's going to be your reading from your angle sensor. And then a, b, and c, those are just going to be coefficients. Okay, now what those coefficients are, we don't know yet. So let's go to this equation here to kind of try and nail down what those coefficients may be. And once we're here, the only thing we need to do is we need to hit submit. And it's going to go off and try and figure out the best coefficients to match up with our curve. So go ahead, submit. It's going to do some fitting data here. It's going to quickly run through that. And at the end of the day, it's going to come up with another menu for us to take a look at. All right, and this is what we're interested in. Okay, really the one I go straight to right away is this coefficient and fit statistics. And so here's the coefficients. Here's the value for A, here's the value for B, and here's the value for C. Okay, and we can kind of see here that it talks a little about standard error, stuff like that. But the key thing is we know our equation. It's of this form, and we know our coefficients. So that's exactly what we would program into our controller. Our function that we program into our controller is this value plus this value times our sensor variable plus this value for C times the square of our sensor value. And then that's going to give us our approximation. So this is kind of how we arrived at, there's our input variable, and there's the value that the function generated using those coefficients. that we found through ZunZun. Okay, so that pretty much wraps up how you could use ZunZun with that percent methane calculation to generate a function that's going to match up pretty good, and we can kind of see here that the difference is very little. All right, we could do the same thing here for the angle sensor. In this case, once again, I'm just going to kind of take my table of data here. I'm going to go ahead and copy that table of data. I'm going to go back to ZunZun here. Just go ZunZun.com, go to my 2D function, go to my function finder, 2D function, text data editor. I'm going to clear out the old data, drop in the new data. Okay. Once I do that, I'm going to go here to my data labels for my graphs, and I'm going to go inclinometer. This is my sensor, and this is going to be angle receiver. So that's correcting for the gravitational pull on my concentrated solar power receiver there. Okay, smoothness control. I'm going to bump this guy to 4 coefficients. And equation families, I'm going to once again get rid of some of these to speed up our time here. Although I could include polyfunctional for a better fit, because most controllers and so on that can work in the solar industry are going to have trig functions. Okay. And I'm going to go ahead and hit submit at this point. And what we're going to see is, once again, it's going to kind of go through, figure out which equations to use, generate some reports here. And we're almost ready. You can see it's come up with some pretty good fits here. So once again, here's the 4 coefficients, A, B, C, and dx that I looked at. I'm going to go to this particular equation. And I'm just going to go ahead and submit here so it can find my coefficients for me. And any second now, it's going to go ahead and find coefficients for that formula. It looks like a few other people are using this site. You might get that server busy every now and then. So once again, you could, if you wanted to, just download your PDF file that covers all this. So maybe you have an audit trail of everything that went on, but you could also just go straight to this coefficient and fit statistics. So this is going to be the formula you'd enter into your controller, and down here you can go ahead and see your coefficients. Okay, A, B, C, and D. Those are the things that are interested. And what I'm going to do is I'm going to follow up this video with a second part that actually shows how I've then entered these equations into my data acquisition system and my controller to take advantage of using this function to correct for essentially my lookup table for the percent methane and for the angle on the receiver. So stay tuned for the second part. Hi there, this is Andrew Brody with Yokogawa's Network Solutions Group, and I'm continuing my follow-up on the curve fitting for renewables videos, where I took you through how to take a table and generate a function that would fit 2 examples. One was for percent methane being used to determine a correction factor for a thermal mass flow meter, and the other was for correcting the angle of a solar tracker such that we could take an angle from a sensor and correlate it to the angle of the receiver for the heat transfer fluid. So what I'm going to take you through now is how you'd actually apply that. And I'm using an example of a data acquisition system. In this case, it's the Yokogawa DAC Master MW100. So this is typically used at places like landfills and other sites where you'd like to collect some data from sensors, maybe do some calculations, totalize flow, stuff like that. It stores data to a up to 2 GB compact flash card, so you can store plenty of data. It can sample as fast as 10 milliseconds, although it can sample a lot slower, which is typical in many applications. It also can do a nice function called math channels, which allows you to take sensor input and correct for real-time stuff like pressures and temperatures, and in this case it allows us to enter our correction function, so we can take in our percent methane from the sensor and automatically generate the correction factor. So let's take a look at it. So the MW100 has a web interface. If you ever want to explore it on your own, you can. We have one online at mw100.us.yokogawa.com. To make any changes, you have to go ahead and make sure everything's stopped here, and you can just pick your stops and hit apply. And the first place I go is my channel settings here. So I go to channel settings. This is where I typically set up my sensors for kind of what's flowing into it. So you regularly set up a sensor here. Since this is just kind of a unit online, not really hooked up to sensors, I'm going to kind of fake out the sensors by using something called a communication channel, which can kind of be used to bring in remote data from Modbus devices or other devices that know how to communicate with the MW100. So I'm going to go back to the channel settings screen here and go to the math channel settings, so we can show how I'll input that function that I found through the ZunZun website. So I'm going to go down to math channels A11 through A20 here. This is where I've actually kind of set up my function here. So what we can do is we can kind of see it's taking the form of A, which is essentially two math constants added together, plus B times this communication channel, which is our X. So two math constants added together, once again, two math constants added together, times my kind of my input value coming through that communication channel squared. All right. And down here I have another math channel that's just showing that communication channel. So this is going to calculate our correction factor, and this is going to show kind of our original input channel that I'm going to use to kind of give us a simulated input for the percent methane. Now, why did I actually use two constants here? One of the reasons is in the MW100, the math constants are only good to 5 significant places. Where the actual math calculation is much more accurate than that. It can go to several more significant places inside the actual calculation. So to get the absolute best coefficient, I went to channel settings here, and I went to math constant settings. And essentially what I've done is I've broken the coefficient into two parts for each coefficient. That way I could recombine them inside of math to get a much larger coefficient than I'm normally allowed to enter. So if we go back here to the math channel settings, we can kind of see that I've just combined the coefficients here to give me kind of one much greater precision coefficient. All right, so there's my A, B, and C coefficients, which are just combinations of two math channels. So once I've got my math channel actually set up, I can then go here to the top, and I can go to display settings, and I can go to display group settings, and I can go ahead and create a group here that contains those two math channels. Okay, so A11 and A12. I can also go to display settings and go to channel tag settings and go ahead and give those down here them a name for the tags for A11 and A12. Then what I can do is I can go back up to the top here, and I can go ahead and I can start my measurement, start my math, hit apply. And I can go to this single screen here. This will allow me to display essentially one group at a time here. And I'm just going to go to my group here and pick curve fit. And then I went over here to digital here to show the digital values. So what's going to happen is it's going to kind of show, here's my curve fit here. And here's my percent methane over here. And we can kind of then see that I've got the 0.0189 at 40%. If I go to my Excel spreadsheet, we can kind of see here's my 40, there's my 0.0189 that the function's supposed to generate. Okay, so let's go ahead and change this. So I'm going to go ahead and open up a second screen here so I can kind of show you how I can change this real time through those communication channels. So I'm going to go to channel settings, COM input channel settings, And I'm going to go down to that C11 that I was using, and you can see how it's 40 here. Well, what I can do is I can say go ahead and up that to 50 and go ahead and hit apply. And if we go back to our single screen here, we can see this is now 50%. We can see that the calculated value for that channel is 0.0212. We can go to our lookup table here, take a look here, and we can see, yeah, it's pretty close, 0.021. It looks like it rounded up too. So we're once again very close here. So I can go back here. Let's pick something like 60% methane at the top of the table. So I hit apply. Go back here. We can see that I'm now computing using the 60% methane. All right, and we can see I'm 0.0228. And let's go take a look. And we can see that there was the original correction factor, 0.022825. We can see that the function is generating 0.0228. And once again, we can see that I calculated 0.0228. Now, what happens if I'm not on the table? Well, let's pick something like, 55.5. Go ahead and hit apply. We'll go back here. We're going to see I've got 55.5 here. And we're going to see that it came up with 0.0222. So let's take a look here at our table. Let's 55.5 is going to be somewhere between here and here. And we can see that that number is definitely between those two. So we can see that it's found kind of an in-between value that's going to correspond to my percent methane. So I don't need to do any special interpolation, if then else logic or so on. I'm just automatically calculating it. So there we go. Here's an example of using the MW100 with that function to do a kind of curve fit approximation of the table for the percent methane correction factor. This is Andrew Brody with Yokogawa Network Solutions. I hope you enjoyed this. Stay tuned for the next video where I'm going to use our HXS10 solar tracking controller to do the function to approximate the curve fit for the gravitational effects on the receiver. Take care. Have a great day. Hi there, this is Andrew Brody with Yokogawa Network Solutions, and today we're going to finish up the example of curve fitting that corresponds with the simplified curve fitting for renewable energy data collection and control paper that I wrote. And in the first part, we talked about using ZunZun.com to generate the curve fitting functions. In the second part, we kind of worked through an example on the MW100 data acquisition system for incorporating the function of percent methane to yield a correction factor for a thermal mass flow meter. And now we're going to work through the second example, which was taking a reading from an inclinometer on a concentrated solar thermal power tracking system and correcting it for gravitational, kind of weight lag on the actual heat transfer fluid receiver. So that's kind of the fluid pipe that runs in front of the collector that's where all the light energy heat gets concentrated on, heats up the oil to then generate steam in a steam plant. So what I'm looking at here now on the screen is just the PDF file that ZunZun allows you to generate. As part of this PDF file that you can kind of keep for your own purposes, it includes a section called coefficients. And so it gives you the formula here. It then gives you the coefficients here. Okay, so these are the 4 coefficients for A, B, C, and D. And in the case of our formula, the X is going to be the input from the inclinometer, and Y is essentially going to be the corrected value that kind of takes into account the lag that we see when we look for gravimetric displacement on the heat transfer piping there. So once we have all this information, I went ahead and just kind of dropped it over to a spreadsheet here, so we can kind of once again see here's the angle coming from the inclinometer. There's the actual angle of the pipe, so we can kind of see that gravity is playing a role on it. And when it's at the other end of the spectrum there at 180 degrees, we can see once again gravity sagging there in the middle. Not too much of a gravimetric effect because it's essentially being nice and supported right in the middle up on top. So there's no angular displacement. Here's the formula here. Here's the coefficients that I've kind of brought into Excel. And here's the results of the calculation. And you can kind of see right at the beginning, there's a bit more error than I'd normally like coming out of this equation, but I'm not too concerned about that because there's not a lot of power being generated that low in the arc of the concentrated. I'm more concerned later on in the day, especially once I get to like solar noon at 90 degrees, that I have very little error. So we can kind of see as soon as we kind of go off of essentially the 0 degrees setting, we start having a very accurate tracking here when we take a look at what the function is returning for us. So the next step would be to take this function with these coefficients and implement it in something like a solar tracking controller. So I have the programming software here for the Yokogawa HXS10 solar tracking controller, and I've gone ahead and kind of built up the equation in here. So the first thing I did is I went and entered my coefficients. So here's the coefficients, A, B, C, and D. This 10 here is just, kind of to the power of 10. And then here's the actual, 10 to the minus 1, 10 to the minus 5, 10 to the minus 7. I don't have a fourth one here because this guy here is just 1.0057. It's not to an exponential of any sort. So once I have all those constants figured out, I go down to my function block programming here. And this is where I can kind of create a quick program to essentially do that calculation. So here's my first power, where I kind of take that value stored in K5, which is 10, and I multiply it by kind of the first exponential there. All right. And essentially, so I go K5 to the power of K6. So in this case, 10 to the power of -1. I then multiply it by my first coefficient. And then similarly here, here's my second one. So I take K2, which is the second coefficient, and I'm multiplying it by CX1. CX1 is where my inclinometer reading's coming into. So it's coming into this variable. This is a Modbus input variable. So in this case, I'm talking off to an inclinometer that actually communicates to my controller via Modbus. Something like the US Digital T7 is a good example of this type of inclinometer. All right, so then I kind of multiply that, I add the two together. So this is the same as A plus BX. And then here's the CX squared. So you can see I'm multiplying the X to get the X squared. And then there's the coefficient being multiplied out. So that's 10 to the power of, -5 in this case, multiplied by the C coefficient, and finally multiplied by the X squared, which is the inclinometer squared. And we can see, once again, I'm doing this for the to the X cubed. So there I'm creating my X cubed. There's my coefficient. So I'm going 10 to the power of -7 multiplied by my D coefficient. I'm multiplying it by the X cubed. And then finally, I'm adding them all together. So you can kind of see here, I've added my A plus BX plus CX squared plus DX cubed. And then I'm finally dumping it into this CY variable, which is just kind of a floating point variable that I can take a look at. All right, so then the next thing I do is I just go communication, and I'd go ahead and I download this all to the HXS10, set it to run mode. Now I've already done that. And so let me kind of show you what it looks like running here. So I'm going to close out some of this stuff, and I'm going to go communication module monitor. It's already running, so I'm going to go execute module monitor. And this will allow me to actually take a look at the function block while it's flowing. So we can see here that my inclinometer has an angle of 50. And essentially, if we kind of flow that down to the bottom here, we're going to see what the corrected angle is. And the corrected angle is 49.94763. So if we take a look here and we go to somewhere around 50, we can see it's 40.94947. So we can see we're really close to the function result that we're looking for. All right, and we can kind of check all the little intermediate values if you want to kind of see where they are. So like we can kind of see what our first coefficient is equaling here. Okay, we can see what our second coefficient is equaling here, 50.285. We can see what a plus bx is equaling here. All right, and so on and so on. We can go and take a look. Let's close that out, and let's go to the register monitor, execute register monitor here. And we can see here's kind of like a watch window, so those familiar with PLCs, controllers, stuff like that, I can literally just drag and drop my values here. So what I did is I kind of dragged and dropped my CX1 onto here, and I dragged and dropped my CY1 onto there. So I can actually go here, double click on this, and force this to another value. So like say I wanted to simulate an angle of 90 degrees coming in from my inclinometer. I could go ahead, hit update there, and CY1 is the output. So we can see we're almost dead on, 90, 90. If we take a look at our sheet here, we can see that 90 and 90 were pretty much exactly where we wanted to be, and there's the function result, 90. All right. Let's take another look at one. So let's take a look at this. So if the angle's reading 30, I'm going to want to read something like 29.9 degrees or 29.898 should be the results of my functions. So if I go back over here, I type in 30 for my angle that I'm reading, we can once again see 29.8979, so 9. So I'm correcting right there. Let's take a look at the other extreme, 180 degrees, and see where we end up. So I put in 180. I'm looking for about 180.25. Let's see if that's close to what the function said it would generate. So if we take a look here, 180, there's the 180.25. 180.2.32 is kind of what we were expecting from the function. And we can see right up there, it's pretty close. All right. So we can see here I'm basically taking into effect gravity using this function generator in the HXS10. So I hope this wraps up our series here, and that you've got a good idea of how you could do some curve fitting for your various projects. It works pretty good. Allows you to kind of interpolate intermediate results without having to use any fancy logic. So once you build that function, you should be pretty good for correcting to whatever you need, whether it's kind of like a % methane flow or angular displacement on a concentrated solar thermal power collector here with something like our HXS10 solar tracking controller. It's definitely got fits in the renewable energy and other spaces. So this is Andrew Brody with Yokogawa Network Solutions signing off, and I hope you have a great week. Take care.